We theorize that in the beginning of the universe that there was hydrogen and helium that got together and forged into stars. Inside the heat of the stars, this is where the other elements were developed. And this is basically the idea of the science, and my good friend William Fowler won the Nobel Prize for discovering this process. The theoretical and experimental studies of the nuclear reaction in the formation of the chemical elements of the universe, and he put together the ideas of this process.
All the atoms in the universe heavier than hydrogen and helium are forged by stars.
In the original universe, floating through space, there was hydrogen and helium. These two elements alone were to make up, later, stars.
Stars are the ultimate alchemists. They turn light elements into heavier ones. They get the energy that they need to glow that way. The star begins its life made out of hydrogen and helium mostly, about 70% hydrogen, 28% helium in the
The hydrogen and the helium floating in space will be drawn together by gravity until it gets large enough under the Goldilocks conditions to produce a high enough temperature to start into the process.
The star's core, the temperature and pressure are so high that hydrogen atoms fuse together to make helium. Hydrogen fusion releases prodigious amounts of energy, the heat and light of a star.
Massive temperatures that will start a type of fusion. A nuclear fusion producing incredible more heat and igniting the star. Then later,
the star runs out of hydrogen and begins to fuse its stocks of helium, making yet heavier elements.
the actual nuclei are then being able to be fused by the fusion reaction, where the combining of multiple heliums to make carbon can happen.
Helium is taken 3 at a time to make carbon.
You can add one more helium to that carbon and make element number 8, oxygen.
That's a tremendous step forward. You get carbon and nitrogen and oxygen made in stars.
And now with the forces, all the other elements up to iron are capable of being made, as the nuclei are being forged together, fused, to make silicon and all the other elements, nitrogen, phosphorus, etc., up to iron.
Now this is great because on the board we already have the principal elements of life.
Organic chemistry is the chemistry of carbon.
Carbon fuses next, and still heavier elements begin to form.
Sulfur, argon, chlorine,
Potassium, calcium, scandium. The pace of this gets faster and faster.
Now the star will contract and expand and eventually get to a place where it explodes into a supernova. And now the incredible temperatures will create the rest of the elements of the periodic table.
In the middle, silicon is starting to burn at 3.5 billion degrees, stupendous temperature.
It makes titanium, vanadium, chromium,
Manganese, cobalt, nickel, and iron.
This is the part of the process of William Fowler. Here he is winning the Nobel Prize in Sweden with the Queen of Sweden. And he came to Youngstown State University and met with me. He was born and raised around Ohio, Youngstown, in Lime, Ohio. He was born in Pittsburgh. And he came and we started to work together on an idea of transmutation in biology.
Iron is really the end of the road. It's sort of the nuclear turnip out of which you just cannot squeeze anymore.
Iron can't fuel the stellar furnace, and so, when a star builds up too much iron, it dies.
The other elements are now forged. We have the beginnings of a universe, planets, and all the forces.
Explosion can be as bright as 4 billion stars like the sun.
A stupendous explosion.
Such outrageous energies overcome the iron barrier, cooking atoms into all the rest of the elements on the periodic table.
The William Fowler spotted a mathematical process based on the laws of mathematics that allowed these atoms to be built. And later we could use this mathematical formula to find out about the trace minerals in the human body.
So starting down here, you can go copper,
Zinc,
gallium,
germanium,
arsenic,
zirconium, niobium, molybdenum, technetium,
strontium,
rhodium,
lutetium,
antimony,
ytterbium,
tellurium,
thorium,
iodine,
radon,
xenon, cesium,
francium,
barium, lanthanum,
tellurium,
cerium,
indium,
actinium,
xenon,
thorium, protactinium,
cesium.
uranium. Done.
All of this based on a mathematical process, needing the right pressure, the right temperature, all based on the science and mathematics that are laid down as the mathematics of life, that later Dr. Isaacs and I will incorporate into biology.
We are all stardust. The carbon in our bodies, the iron in our blood, the calcium in our bones. Every last atom was formed in a star.
All of the elements of the periodic table all come together and made kind of a nice little song.
What's the universe made of? I am so glad you asked.
There's antimony, arsenic, aluminum, selenium, and hydrogen, oxygen, nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, urethrium, uranium.
Nickel, neodymium, neptunium, germanium. Everybody! And
Zirconium, lutetium, vanadium, and anthium, and osmium, and astatine, and radium, and golden protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, and terbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium.
There's yttrium, terbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium.
iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium. Just the Asians. And lanthanum and osmium.
Cadmium, and calcium, chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, isinium, nobelium, and argon, radon, neon, and argon. Hold on, quiet.
There's gold and californium and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
If you didn't get that, let's play it one more time so you can see it on the chart and the mathematics.
Antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and golden protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium, and helium, and hafnium, and erbium, and phosphorus, and francium, and fluorine, and terbium, and manganese, and mercury, molybdenum, magnesium, dysprosium, and scandium, and cerium, and cesium, and lead, praseodymium, and platinum, plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, and chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. Thank you. You may be interested to know that there is an older, much earlier version of that song, which is due to Aristotle, and which goes like this. There's earth and air and fire and water.
The mathematics of this periodic table, the elements, how they were structured in their energetic way, would allow us to understand electron transport chains in biology and allow us to understand about biology and the trace minerals of biology. So as we see here from the 1983 Nobel Prize on the formation of elements, there's a mathematical principle. Now, a long time ago, way back in 1869, the Russian man Mendeleev, just by observation, saw that there was atoms. Didn't know anything about atomic structure or anything about that, but he could propose an entire periodic table based on the relationship and the formation. He actually predicted atoms that we discovered later. It was amazing. So I worked with Dr. Isaacs with his book, Complementarity in Biology, and tried to find a way to predict this mathematical relationship beyond just atoms into biology. Worked with Albert St. Georgi, and he had the idea of the math principles of this electron transport chain. So it was amazing to be able to find a way that we could really intimately understand biology. Working at Youngstown State University, I started to put together the book, The Promorpheus. I started to understand metabolism, reproduction, and all of the little intricacies about how energy, mass, charge, momentum, heat, all these different things were going to be handled and exchanged through mathematical principles. And then to put it onto a matrix so we could start to understand how atoms could share electron transport and accomplish the different things. And Isaacs imposed this very complicated matrix that we started to develop. Here's the electron Poisson curve, so we could see how electrons could work. And vitamin C sits right in the middle of that. And we started to understand the different elements and how they were needed. So I published this in the Promorpheus in 1982. Now, of all the different scientists I worked with Chalier and William Fowler and St. Georgi and many, many others, we're able to start to understand more about biology. And Rutherford had discovered a transmutation of the elements, being able to make different elements. And Kervran had an idea of biological transmutation, and how biology was going to be transmutating the elements. And that he found that in eggs, if we take eggs fresh from the chicken and destroy them, there's a different quantity of the atoms if we let them gestate for a long period of time. So biology was doing this. Now, after winning the Nobel Prize, William Fowler came to Youngstown State University to do a lecture. And as he lectured, I asked him the question. I said, could it be that we could transmutate the elements in biology? And at first he said, no, no, no. Then he said, well, wait a minute. He said, there's a possibility that through slow neutron capture, we would be able to do this with certain elements. So it was actually fantastic. William Fowler and I worked together on a paper, and were able to show that there was a way that biology could transmutate the elements. Very exciting. Has never really been accepted by modern science and physics, but I think it should be. It should get another look. But using this idea of his matrix from the 1983 stellar formation of the elements, and using it with Isaac's matrix, we can start to see the similarities. And this came into a whole new idea of handling the minerals and handling the idea of the trace minerals. So I put this together in 1982, and then having produced it, people had read it, and I got nominated for the Nobel Prize for this work. I presented this work at the Nobel Prize Hospital in Stockholm, Sweden.